Hi, welcome to Chapter 11, Part 2, Thermal Energy and the Ideal Gas Model. We were first introduced to the concept of thermal energy in a previous chapter. Let's just review this right now. Thermal energy is the total amount of energy inside a substance due to all the kinetic energy and potential energy of all the atoms vibrating. Like all forms of energy, thermal energy is measured in the units of joules, and the joule is named after James Joule, the English physicist. So in this animation down here, this is giving us an idea of what thermal energy is. Remember that our model, if we think about a solid, for example, the atoms in the solid are connected by bonds, atomic bonds that hold the atoms together and make it a solid. These bonds behave like springs, okay? And we talked about this earlier in the course. So these bonds then cause the atoms in a solid to vibrate and wiggle and jiggle back and forth. And remember that thermal energy is basically this motion of the atoms jiggling back and forth. There's kinetic energy due to the motion or the wiggling of the atoms, and then there's also potential energy, which is stored in the bonds, which, remember again, is you can think of that as an elastic type of potential energy. So related to thermal energy is the concept of temperature, which you're probably somewhat familiar with. Temperature is a measure of the average kinetic energy per atom or molecule inside an object. And we measure temperature in units of degrees. And there are several different temperature scales that are used. For example, there's the Celsius scale, degrees C. There's the Fahrenheit scale, degrees F or Fahrenheit. And then there's the Kelvin scale. So we'll be talking a little bit more about these various degrees and temperature scales shortly. Now, regarding thermal energy, what this means is that at high temperatures, we have, based on our definition here, high temperatures just mean we have lots of kinetic energy, and lower temperatures mean we have less kinetic energy. So let's take a look at a solid, for example, at low temperature. So in this little animation here, we see the atoms in the solid. They are vibrating, but relatively slowly. And this would represent a solid at a low temperature. If we raise the temperature of this solid, for example, we place it over a flame or stick it in an oven or even put it out in the hot sun, the temperature of the solid increases. And the reason for this is that there's more thermal energy in here now, and we see that the atoms of the solid are vibrating faster and with greater amplitudes as well. So this is the difference between a high temperature solid over here on the right and a low temperature solid on the left. It's just the amount of thermal energy, kinetic energy inside the substance due to the atoms shaking and vibrating. We can have a similar type of phenomena here if we look at a gas. At low temperature, a gas is represented here in this picture as these are the gas atoms that are flying around inside this container, but they're flying around at relatively low speeds. In other words, they don't have a lot of kinetic energy. Now, if we heat up the gas by placing a flame under this is a sealed container, now the gas atoms are flying around at a faster speed. They have more kinetic energy. So more kinetic energy means a higher temperature. So you can see on our thermometer here, it indicates a higher temperature. So again, this is the difference between a hot gas and a cold gas. All right, the higher temperature gas just means that the atoms inside the gas are moving at a higher speed and they have more kinetic energy. We're now going to talk about a concept of a temperature called absolute zero. So let's go back to our animation here of a solid. And think about what would happen to the atoms as we keep cooling down the temperature lower and lower. Well, remember, if the temperature becomes less and less, that means we're taking away the thermal energy. So we're removing thermal energy from the solid as the temperature drops. And you can see in this animation here, the atoms in the solid are, they are wiggling still and vibrating, but they're vibrating relatively slowly and, barely moving back and forth. So this would represent a solid at a very low temperature. In theory, if we could keep lowering the temperature here, like place this in a special type of cryogenic chamber or freezer, in theory, if we could remove all the thermal energy, these atoms would actually stop. And this is the temperature that is called absolute zero. It's the temperature on the Kelvin temperature scale at which the atoms have lost all their thermal energy, meaning they're not moving at all anymore. So absolute zero is 0 kelvins. Okay, that's 0 degrees, on the Kelvin scale. On the Celsius scale, or centigrade scale, it's minus 273 degrees Celsius. Or in the Fahrenheit scale, it's about minus 459 degrees Fahrenheit. Now, by the way, the unit Kelvin is named after Lord Kelvin, an Irish physicist who studied thermodynamics. So one question that comes up here, can we keep cooling down to get below absolute zero? So in other words, once we reach absolute zero here, what if is there some way to cool down this substance even further so that it's colder than absolute zero? What do you think? Well, the answer is no, we can't, because remember the definition of absolute zero is that means we've removed all thermal energy from the solid. So once we've removed all the thermal energy, by definition, that is the lowest possible temperature there is. We cannot go any lower than absolute zero. I mentioned a couple slides ago that there are 3 commonly used temperature scales, the Fahrenheit, Celsius, and Kelvin scales. So let's just take a look at these briefly and see how they compare. This thermometer shown here on the left is calibrated to Fahrenheit degrees. The one in the center is a Celsius thermometer, and the one on the right is calibrated to kelvins. So a couple of the interesting features here is that the Fahrenheit scale here, let's start with this. The freezing point of water is defined as 32 degrees, okay? And this is just sort of an arbitrary assignment that was made for this scale. Likewise, the boiling point of water was assigned to 212 degrees Fahrenheit. Room temperature, you can think of 68 degrees is probably a typical room temperature, or maybe 80 is a somewhat warmer room, okay? But those are all temperatures in the Fahrenheit scale, and the lowest possible temperature on the Fahrenheit scale is absolute zero, which is about negative 460 degrees Fahrenheit. Now, if we go to the Celsius scale, the way the Celsius scale was calibrated and defined is the freezing point of water was set to 0 degrees Celsius. And again, this is just an arbitrary assignment. So we're sort of using water here as our reference point for the Celsius scale. And, what's so special about water? Well, nothing particularly. It's just this was a common substance that they decided to use for this temperature scale. So 0 degrees C is the freezing point of water, and they also chose 100 degrees C as the boiling point of water. So room temperature is somewhere around 20 to 27 degrees Celsius. That's the temperature probably in your room right now where you're sitting. Absolute zero on the Celsius scale is negative 273. Now let's go to the Kelvin scale here. So the Kelvin scale is what's used most by scientists, and the reason for this is, remember that temperature is related to kinetic energy of the substance. The more kinetic energy the substance has, the higher its temperature. Kinetic energy is always positive. right? Remember, kinetic energy is equal to 1/2 mv squared. Well, mass is always a positive quantity, and velocity squared is always a positive quantity. So in other words, temperature should, in a sense, be always a positive quantity. And that's what the Kelvin scale does. It doesn't use any negative temperatures, because a negative temperature, as is seen over here on the Fahrenheit and Celsius scales, they don't really make sense from a physical standpoint. So the Kelvin scale starts at 0. That's the lowest possible temperature, and of course that's called absolute zero. And temperatures only can increase. They can only go up. They can't go down from 0. So the freezing point of water is 273 kelvins approximately. Room temperature, right now you're experiencing probably somewhere around 290 to 300 kelvins. So, that sounds like a lot, right? But that's just room temperature. And then the boiling point of water is 373 kelvins approximately. So the important thing that we're going to be doing in this chapter and the next chapter is we're going to come up with some various laws for the behavior of material, solids and gases in terms of their thermal properties. And most of the time, we're going to be working with the Kelvin temperature scale. So one thing that we'll have to do fairly often is make a conversion between a Kelvin temperature and a Celsius temperature and vice versa. So, and it's actually quite easy. If we know the temperature in Celsius and we want to go to Kelvin, all we do is add 273. If, on the other hand, if we know the Kelvin temperature, or absolute temperature as it's called, and we want to convert that to Celsius, we just subtract 273. So that's really all we're going to have to do. The conversion between Fahrenheit and Celsius, those are more a little more complicated. There's a fraction involved, and you have to add a constant. You can look those up, but we're not going to be doing those in this course. But we will be going back and forth between the Celsius and Kelvin scale using these relationships right here. So we've seen these two concepts, temperature and thermal energy, and they are definitely related to each other, but they are certainly not the same thing. Just to summarize, remember, temperature is an indication of the average kinetic energy inside of a substance for each atom, whereas thermal energy is just the total amount of energy inside a substance. So there, in that sense, we have to add up all the kinetic and potential energy of each atom. So let's just go through. This is sort of a conceptual quiz here. For each of these pairs of items, let's try to think about which item has the higher temperature and which item has the greater thermal energy. So for example, let's start with this one. If I show you a hot potato and a cold potato, which one of these has higher temperature? And then think about which one has greater thermal energy. So go ahead and pause the video and think about that, and let me know, or remember your answers. Okay, so in this first one, it's pretty basic. Obviously, the hot potato has a higher temperature because it is hotter, okay? And likewise, the hot potato has more thermal energy than the cold potato because if we added up all the energies of all those atoms inside the potato, the hot potato would certainly have more thermal energy because, remember, each of those atoms is moving around faster. It has more kinetic energy. So this first one was kind of an easy one to get us started. Let's now look at this one. Let's compare a hot potato versus a cold lake. So what is a cold lake? Well, think of like a lake in Canada in the winter where it's got ice on top and the water temperature is barely above freezing, right? You wouldn't want to stick your feet in it. It would hurt your feet. It's so cold. So let's compare these. Go ahead and pause the video and think about which one has more higher temperature and which one has more thermal energy. Okay, so for temperature, again, this is pretty simple. The hot potato, which comes out of your oven, might have a temperature of, let's say, 350 degrees Fahrenheit, right? The temperature of your oven. The cold lake, on the other hand, might have a temperature of maybe 35 degrees Fahrenheit. So the hot potato certainly has much higher temperature than the cold lake. But what about thermal energy? Well, it turns out that the cold lake has much, much more thermal energy than even the hottest potato you could imagine. And the reason for this, remember that thermal energy depends on the total amount of energy inside the object. So a lake has so much mass, it has so many more atoms compared to a tiny little potato, that the lake is going to have a huge amount of thermal energy, even if the lake is very cold. All right, last one here. Big hot potato versus small hot potato, and assume that they both came out of the same oven. So go ahead and pause the video if you want and think about the answer to this one. All right, well, so if these two potatoes were both inside the same oven, then their temperatures would be equal. Neither one of them has a higher temperature, right? The temperatures are the same. However, for thermal energy, the big hot potato would definitely have more energy, more thermal energy than the small hot potato, just like the cold lake did here. The reason here is that the larger hot potato has more mass, it has more atoms, therefore it has more total energy, which is thermal energy. The remainder of this part of the video, we're going to talk about what's called the ideal gas model. And this is a way that we can study and predict the behaviors of gases. Now, this is a good time to also briefly discuss the concept of a model. So a model in science, remember, is something that sort of oversimplifies the actual picture. The reason for this is so that we can use the model and understand the behavior of the system. So in this case, we're talking about a gas. And gases don't always behave exactly like this ideal gas model, but they behave very much like it. Okay, so in other words, this ideal gas model is pretty accurate. It works very well, and we don't have to take into account a lot of the complicated situations that come for real gases. So we are going to model gases as if they behaved like an ideal gas, and that's the idea behind this model. So what is the ideal gas model? Well, we think of the gas as made up of a large number of atoms, and each one of these atoms has the same mass, m, all right, and they're identical, and they're all zipping around, moving around inside this container randomly. And you can see, in the picture over here, the animation, you can see the gas atoms moving around. The atoms in the gas are relatively far from each other, and they interact only rarely when they collide. So you can watch again in this animation. Every once in a while, you'll see some of these gas atoms slam into each other. And also, when they strike the edge of the container here, they bounce off of the container here. So that's the only time that they interact. We're not going to model any type of attraction or repulsion between the gas atoms. The only time they know each other or even in there is when they bump into each other. And the third part here, when they do bump into each other, they behave like hard point-like spheres. So you can think of these sort of like billiard balls on a pool table. Whenever they bounce, interact, they bang into each other and they bounce off of each other elastically. So these are elastic collisions. No energy is lost in these collisions. All right, they're not sticking together. They bounce off of each other like you can think like hard rubber balls or something like that. So our next goal here is to come up with a relationship between the temperature of an ideal gas and the energy of the gas atoms. The actual theory that is used to prove these results is called kinetic theory, and we're not going to talk about that in this course. So I'm just going to be showing you the results. In your lecture notes, I do have some of the details there if you're interested, but you don't have to go through that for this course. So let's talk remember, let's review real quickly here our definition of temperature. Temperature is proportional to the average kinetic energy of all the atoms. And what we're actually talking about is the translational kinetic energy, not the rotational kinetic energy here. So our definition of temperature, again, is that temperature is proportional to, and that's what this symbol means. Temperature is proportional to the average kinetic energy of all the atoms in the gas. Now, in a typical container of gas, all right, like something even as small as like a test tube, there are trillions and trillions of gas atoms in there, and they all have different speeds and velocities and directions as they're flying around in there. It's random, so we can't. There's no way we can keep track of trillions and trillions of individual gas atoms. So instead, what we deal with here are statistical parameters, such as the average kinetic energy. That's much more important because that's going to tell us about the behavior of the gas. We don't care what individual gas atoms are doing. All we care about is the average. And so, the study of thermodynamics is closely related to statistics. The actual relationship of this, instead of T being proportional to K average, here's the actual result from kinetic theory. It says that temperature is equal to 2/3 times the average translational kinetic energy per atom or molecule divided by a constant. And this constant is called Boltzmann's constant. So it's designated as K sub B, B for Boltzmann. And this is named after Ludwig Boltzmann, the great Austrian physicist who worked on thermodynamics. So this, and by the way, in this relationship here, temperature, this is the absolute temperature of the ideal gas. Now, what do we mean by absolute? That means we measure it in kelvins, all right? That's where we're going to use the Kelvin scale here. You can see that if the kinetic energy here, the average kinetic energy, is 0, what does that mean? Well, this whole right side of the equation would be 0. That would mean the temperature would be 0 kelvins. And that, of course, is absolute 0, meaning there's no energy in the atoms of the gas. So we can use the results that we just talked about on the last slide to come up with a relationship between the temperature and the thermal energy of an ideal monatomic gas. Now, by the way, here's a new term for us. Monatomic, that means a single atom. So these are not molecules like the oxygen that we breathe is O2. Also, it has nitrogen in the air, which is N2. All right, though that's a molecule of 2 atoms of nitrogen or oxygen bonded together. We're going to be talking here again. This is to keep things as simple as possible. This is an ideal monatomic gas. We're going to treat a gas as if it consisted of individual particles, okay, not molecules connected together. So anyway, our result from the last slide was temperature, absolute temperature, is equal to 2/3 K average divided by Boltzmann's constant. We can solve this for the average kinetic energy. So the kinetic energy average is equal to 3/2 times Boltzmann's constant times the absolute temperature. All right, so what this tells us here, if we know the temperature of the gas by measuring it, let's say with a thermometer, we can figure out what the average kinetic energy of each of those gas atoms is by using this equation here. We know what Boltzmann's constant is, right? It was I talked about that in the last slide. It's a number, very small number. So now suppose we have a sample of this gas that contains N atoms. So what is N? Well, N is usually going to be a very, very large number. Again, it's going to be something, trillions and trillions of atoms. The total kinetic energy then is given by the total kinetic energy is the average kinetic energy, K average, times the number of atoms N. So for an ideal monatomic gas, there's no potential energy. It's all kinetic energy because we've just got these gas atoms flying around. There's no bonds, atomic bonds holding it together like in a liquid or a solid that would store potential energy. So since all of the energy is kinetic energy, then the thermal energy is just equal to this total kinetic energy here. So the thermal energy of a gas, E thermal, is equal to N, the number of gas atoms, times the average kinetic energy per gas atom. And remember, that was given by this up here. So putting this all together, the thermal energy of an ideal monatomic gas is given by 3/2 N K sub B, which is Boltzmann's constant, times the temperature of the gas. So this is we can calculate the thermal energy of a gas now. All we need to know is the temperature of the gas, which can be measured, of course, with a thermometer, and we need to know how much gas is there, how many atoms are there, okay? And we'll find, as we go forward, we'll figure out other ways to measure this as well in this chapter and the next. But for now, this is where we're going to start. And again, just a note here, this is valid for monatomic ideal gases. Some examples of monatomic ideal gases are gases that they don't interact with each other, such as the inert or noble gases, helium, neon, and argon, to name a few. The formula that we just talked about on the last page can be easily modified to account for changes in temperature and thermal energy. So this is the same formula we just saw in the last slide, except now we put a delta sign in front of the thermal energy here, and we put a delta sign in front of the temperature over here. So what this formula now means is that on the left here, delta E thermal is the change in thermal energy of an ideal monatomic gas caused by a change in the absolute temperature of the ideal gas. And this, of course, remember, this has to be in kelvins here, all right? And here, there's a constant 3/2. N is the number of atoms, and once again, K sub B is Boltzmann's constant, which is equal to 1.38 times 10 to the minus 23rd joules per Kelvin. Notice Boltzmann's constant is a very, very small number here. So let's go through an example here to see how we can use this result. So your car contains about 10 to the 25th power of molecules in it. All right. So again, when we deal with molecules in a gas or atoms in a gas, we're always going to be talking about really, really large numbers, right? This is the number 1 with 25 zeros after it. Another way to think of this is 10 trillion molecules of air. Now, what do we mean by molecule of air? Well, what we're breathing is mostly nitrogen molecules, N2, and oxygen molecules, O2. Okay, so suppose on a sunny day, the inside of your car heats up from 80 degrees, which I converted that here, 27 degrees Celsius, to this is a really hot 135 degrees Fahrenheit, right? This is like on a hot day when you leave your car out in the sun for a couple hours and you open up the door and it feels like an oven in your car, right? So this is a realistic temperature here, 135 degrees Fahrenheit, which is 57 degrees Celsius. So part A, estimate how much thermal energy the air inside your car initially has. Model the air as an ideal monatomic gas. All right, so notice what we're doing here. We're not going to get an exact answer here. This is going to be an estimate. And the reason for this is we're going to model the air as if it were an ideal monatomic gas. But it's not, right? The air is actually diatomic. It's nitrogen, which I mentioned is N2, and oxygen, O2. Those are diatomic molecules that each contain 2 molecules. But we're not going to deal with that in this course. That makes things a little more complicated. So let's just work with this ideal gas model that we're describing here. So the first, let's do this part A first. The first step is to convert temperatures to Kelvin. So the initial temperature of the car was 27 Celsius. Remember, to go to Kelvin, we just add 273. So that's 300 kelvins. So for part A, the thermal energy inside your car is 3/2 N K sub B times the initial temperature. So N is the number of atoms, 10 to the 25th. Boltzmann's constant, here it is, that number there. And then the initial temperature is the 300 kelvins. So on your calculator, you just have to multiply all these numbers together. 3/2 is 1.5 times this number, times this number, times this number. And of course, make sure you know how to use scientific notation on your calculator, and you'll get the number of joules there is 62,100 joules of thermal energy. Now, part B, how much thermal energy was added to your car from the sun? So what we're looking for here is the change in thermal energy. So remember, delta E thermal, it's the same formula as here. It's 3/2 N K sub B times the change in temperature, delta T. So the only thing different here is that this delta T, we have to figure out how much did the temperature change. Well, we were told that the final temperature was 57 Celsius. So if we add 273, that's 330 kelvins. So the temperature went from 300 kelvins up to 330 kelvins. So our change in temperature in kelvins is 30 kelvins. That's where that number comes from. All the other numbers in here are the same as they were in part A. So this comes out to be 6,210 joules. So basically we see that the thermal energy of the air in your car increased by 10%. And the reason for that is that the temperature increased by 10% when we talk about the Kelvin temperature, right? 300 going to 330 is a 10% increase. So that is it for this part of the lecture. I will see you in the next part shortly. Goodbye.